Okay, so today's question is 146, LRU Cache. The question asks us to design and implement a data structure for least recently used cache. So it's a cache for key value pairs, and it will support two operations, put and get. The get key just return the value associated with the key, and if the key is not in the cache, we return -1. The put key value here is just inserting the key value pairs into the cache. If the key is already in there, it will update the value for the key. And the cache also has a positive capacity, meaning the number of maximum number of key value pairs it can store. So when the cache is reaching its capacity, it should invalidate the least recently used item before inserting a new item. The item here is the key value pairs. So the least recently used item, in order to determine that, you can imagine we could use some kind of timestamp or to indicating the last time every key value pair is used, or we could just rely on the ordering of the items within this collection, the data structure, to tell us which one is least recently used. And you know that the clock is not usually trustable, so we can pretty much we should pretty much use a method that relies only on the ordering. So the requirement is really to have get and put both in constant time. So yeah, I'm gonna use an example to show some insights about how this works. I'm not going to use theirs because it's a little bit short, so there are interesting properties that I think it's not so obvious with their example with capacity too. Anyway, I'm still going to show, I'm going to just show the put and get part here. So let's say that we have a cache with capacity 3. So you can imagine it will look something like this, a collection with 3 slots possible. Capacity equals 3, and we're gonna do put 1 1, put 1 2 2, and put 3 3. So after this 3 operation, the internal of the LRU cache looks something like this: 1 1 2 2 and 3 3. It's just like a stack or a queue, just append to the end. So after that, when we do get 1, it should return the value associated with the key 1. So it's 1 here, and what it will also does is to help us to identify, rearrange the key value pairs within this cache to still be able to tell us which key value pair is least recently used. So if you can imagine, there is a timeline here. Okay. Recently used. By used we mean either put or get. After we do get 1 1, we will actually promote the 1 1 from the its original location towards the end. And if we do put 4 and 4, because we have already reached the capacity, we actually do this in 2 steps. We do remove, evict. I don't know how to spell evict, so I'm gonna do remove to empty that slots, and then basically a put. Again, do a put. So this time we'll put the 4 4 in here. So this put method is actually 2 steps. If it's not empty, we remove. If it's reaching the capacity, we'll actually do a remove before we do the actual put. And also we can update the values for the key. So let's say that we want to do put 1 5. What this does is gonna do two things. Do update. We're gonna update the value for the key 1 to be 5. Then we're gonna rearrange it to rearrange this to move it towards the end, because it's now the most recently used. So that's pretty much the how the data structure works when you interacting with it with put and get method. So let's start think about what data structure under the hood we need in order to have some of the constant properties in doing all of this. So one thing that's obvious is that we want to access the tail element in constant time, because that's where that's needed when we do put and this move here, right? Actually, we need constant access to both head and tail, because when we actually do the remove, we remove the head element. So we can do this with either array or linked list. Linked list with the 2 pointers, the head and tail pointers, so that we can access the head and tail in constant time. For array, we can just calculate the end location with the capacity, and we also need to be able to move an element like a 1 5 towards the end in constant time. So this would eliminate the options for array, because for array you essentially is swapping it. So if we move 3 3 towards the end, we essentially would do do swap and another swap. So it's a linear time operation to do the move. So we want we basically narrow down this option to be doubly linked list. The reason for it to be doubly linked list is that if we can somehow magically grab this middle element 1 5, we need to be able to while 3 3 2 4 4. The only way we can do so is to have a previous pointer and a next pointer, so that we can once we know 1 5, we can grab 3 3 and 4 4. So that leads us to constant access to nodes, to the nodes in the linked list. This is done not by the linked list itself, it's done by a hash map. So the key is the key value. It's the key to node. So with this, we pretty much become as this is pretty much the design for this data structure. Which supports the requirement, the constant time complexity for both put and getting all these different flavors of it. So yeah, I'm gonna cheat with a really quick implementation with Python, because the ordered dictionary from collections is basically hash map plus doubly linked list. So use that to implement this. Is pretty simple. I'm gonna use C++ to do the hash map plus linked list implementation, but the Python one is just gonna show the get and the put, how you just show that more clearly, how the basic logic behind get and put, also the move, how that works. We would do C++ code afterwards, which explains, which shows how these two things work together to support this a little bit better. So one higher level to show the big idea behind put and get. Another implementation which is a little bit lower in level to show how these two things work together. So what we're gonna have here is capacity, store the capacity so that we can testing the capacity in the put method, and the cache itself, it's ordered the dictionary, and the get method is we check the key, if the key is in the cache or not. If it's in there, we just return the value. No, if it's not in there, we return -1. If it's in there, we need to do the move. We have to make sure the recently accessed key value pairs to be moved towards the end. So what we would do is to move it to the end. And then we return the value for that key. Let me move my mouse to unhide this. So it's pretty much the interaction with the get method. Then for the put method, we'll first test if we reach the capacity or not. And also the condition also involves whether we need to do actual insert. So it's two things on this condition. So it's self equal the capacity and the key not in. So when we are reaching the capacity and we definitely needs to insert a new item, key value pairs, then we need to remove the least recently used one. Papa item. So yeah, we remove the last equal to false. We remove the first one. So the first one being the least recently used. I should point at yeah, here we remove 22. So that's the first one. Then we do the self cache key equal to value. This handles insert as well as the update for value. After the update or insert, we move it towards the end. So yeah, so this is the implementation using order dict from Python. Let's see if it works. Okay. I think it should work. I submitted like 20 minutes ago to do a quick testing. So yeah, it's working and it's quite fast. It just uses a lot more memory than other options. So a quick note before we go to the C++ is that I don't like this actually, because it's all we use is the stuff from order dict. So we'd better actually just inherit this. And just subclass this order dict to you know, it's more. It should be. I like it more. So so we change this to self.keys. We return -1, and instead of calling this, we calling the super. This is super under get item key. For this, it's self.keys. Super. Nope, set item. So let me quickly check if I have problems. The constructor set the capacity, and then for the get we check the key, move to the end, return the value. If we reach the capacity and we definitely need to do an insert, we will pop the item, then we will update the key value and move that to the end. So yeah, it looks nice, it looks good. So try to submit this one. There should be no difference, but somehow it's slower. Yeah, I like this better because there is really not much other than using the stuff the front order dict. So I think subclasses is more reasonable. Yeah, so let's switch to C++ and we will do the hashmap plus doubly linked list implementation. Alright. So okay. Capacity. We're gonna have a hash map, unordered map, which is an integer to a linked list of integer to integer, and we are storing the reference to the individual nodes in there. So we could use the iterator. Let's call it map, and for the list itself, we'll just call it L. This will be M for short. Nope, this should go into private. And in the constructor, we basically just set the capacity. So let's handle the get first. It's similar to the Python code, really. If the key is not in there in the map, then we just return -1. We don't need to go into the doubly linked list to grab the value. Otherwise, we use the splice method. Begin lm key. So what this does is to grab a reference to the node containing the key value pair within the doubly linked list, within this doubly linked list, and move that towards the beginning. Then we need to return the linked list is the stuff on it is a tuple. so that we can the first item will be the key and the second item will be the value. So that's how get works. It's actually quite similar to the Python code. Let's do the put then. Let's stick with the Python logic. If we are reaching the capacity and we don't have the key, then we need to erase the sorry, we need to pop the least recently used item from the linked list. And we also need to remove the association between the key to the node. The first item in the pair is the key, so we need to remove that from the hash map. And after that, we should just do the update and insert update, and so it's so if we'll do the update first. If the key is in there, we should the update is basically delete the old value, delete the old value and then insert a new one. So we could do delete and then do insert. Also update the association between the key, the hash map, and the linked list. So let me see if we have problems. We have a doubly linked list L here, which is the key value pair, stores the actual key value pairs. We have a hash map which stores the key values, and it's a reference to the nodes inside the doubly linked list. The double linked list have a capacity which is set it by the constructor. When we do the get method, it will try to check whether the key is in there or not. If we have the key, then if we don't have the key, we return -1. Otherwise, the key is in there, so we move that particular node in the doubly linked list towards the beginning. Here, the beginning is the right hand side, the back is the left hand side, and then we return the value for that associated with that key. So this get looks right. Let's look at the put method. If we reaching the capacity and we don't have that key, what we do is to we need to pop the least recently used key value pairs in the doubly linked list. We also need to remove the association between the key value to the node. So that's and we do this in this order. We remove the association first, and then we actually remove the key value pair. So this looks right to me. And then the very last thing is this put. So if we do have a key value pair in there, we definitely would want to maintain the association But since we are, no matter we are doing insert or update, the new key to the node association is going to be towards the the final location. So we do so we just delete the old key value association in the doubly linked list and just put a new one here, and then rewire the association. So it looks right to me. So let's try submit this one. Wow, geez, it's quite slow today. Yeah, that's because context has started. It's sad that it's slow, but this is using doubly linked list and the hash map combination of the two. So I guess compared to the Python code, even though it's two data structures separately and work together in the code here, compared to using the ordered dictionary, the code actually does not differ a lot. So if you can go back and forth, compare this to the get, almost look identical. The put, it's a slightly different. In the ordered dic, you only need to do one line. I guess in one line for each section, right? Let me switch back to see. Yes, one line here, and set item move to the end. In the the get is 3 line, the put is 4 line. In the C++ version, the get is also 3 lines, and the put is 1, 2, 3, 4, 5, 6, slightly longer. But anyway, it's showing you the how this doubly linked list and hash map actually work together to provide the what the doubly linked what the order dicta gives you. Anyway, this video is too long. I hope it's helpful, and bye for now. I'm gonna join the context as well.